Welcome to this lecture on identification of the dynamic coefficient of the dynamic model of the robot. So we have derived so far a complete symbolic expression of the dynamic model, including inertial part, Coriolis and centrifugal part, gravity. If we wish, we include also some model of friction effect, so non-conservative torques, and then on the other side of the dynamic equation, the input torques provided by the robot. If we would like to use this dynamic model, we should put inside numbers. Numbers not related to the motion. This is something that we would like to specify or measure with encoders and with sensors, but in fact, dynamic parameters related to the links. The most simple case that we can consider is the case of a single link moving, let's say, with some torque in the horizontal plane. Now, the model of this system can be written in the following form. We have written inertia around the center of mass, so we will have a center of mass here, some distance here, the length is L, the mass is M, and after computing the kinetic energy, potential energy is constant, so it's gone. Eventually, we will have a coefficient multiplying the acceleration of the joint equal the torque. So if we would like to do some simulation or just compute inverse dynamic, we should know this number. So why only this number? In fact, this link is characterized by a number of dynamic parameters. First of all, the mass m, then the center of mass position with respect to some reference frame. This reference frame may be placed here, or here, or here. In fact, we don't care too much, but the only number that matters is the distance of the center of mass with respect to the rotation axis. So this d, and in particular, it appears here with a d square. And then the inertia around this axis, the axis passing through the center of mass itself. Why I'm writing things in this way? Because this is the scalar inertia of the robot, of this single link in this case. And we have seen using Koenig theorem that we would like to express the kinetic energy as the sum of the linear kinetic energy due to the fact that the center of mass is moving at a certain speed, vc, plus the angular inertia, angular kinetic energy, which is related to the angular velocity of the whole body, considering the inertia through the center of mass. So this is why, in this case, we are using EC. So these are the three numbers. In fact, the inertia of the link is a 3x3 constant matrix, 3x3 symmetric. So 6 numbers. The position of the center of mass is in fact a vector going from any reference frame to the center of mass. So in general, it's three-dimensional. And the mass is a scalar. So if we have a number of considerations to make here. First of all, if we start with a generic link, this pointer, this body, we have 10 numbers to be considered as a list of dynamic parameters. But when we place this link at this joint axis and we let it rotate and we want to consider the dynamics in this situation, we see that only 3 numbers appear out of the 10, and this d square is just one component of this vector. Not only that, but they appear in a combined way, and in fact in a nonlinear combined way, because d appears in a squared fashion, and as a sum, as a result, only this dynamic coefficient, we will call this coefficient, matters for the dynamics. So this is a very simple case, and when we would like to do again dynamic, direct dynamic or inverse dynamic, we should know, in fact, this number, this and only this number. So how can we generalize this simple case? For instance, if we put the link into the vertical plane, so we have the gravity effect, there will be an extra term appearing here, of the form mg0d, let's say, sine of theta. So again, we have a second dynamic coefficient, mg0d, which includes the gravity acceleration, the mass, which was one of the dynamic parameters appearing here, and the distance of the center of mass from the rotational axis. But again, what matters is only this product. In particular, if we assume that G0 is known, md, which does not appear here as such. So we would have 2 dynamic coefficients to be known, either given from some CAD or identified. So again, how does this rule generalize? So we will see that there's a fundamental property in the dynamic model of any robot, namely its parametrization in terms of a number of dynamic parameters, and this parametrization is linear. It's not an approximation. In fact, you see that these 2 numbers appear in a linear fashion once we have combined them. In fact, we will talk about dynamic parameters and dynamic coefficient, which will be the result of a combination of dynamic parameters. And the property is that the system is linear in a certain set of dynamic coefficients, and we would like to derive this set in an automatic way, and also illustrate the procedure for identifying those numbers through experiment. So this block of slide will deal exactly with this problem. So let's start from scratch, consider not just one link, but in fact a generic link moving, translating or rotating around the joint axis I. So we have a number of quantities that we have defined. So what matters is the total mass. In particular, we will use the subscript I because we refer to link I. So the mass mi, the location of the center of mass RCI with respect to any frame attached to the link, for instance, the Dynavit-Hartenberg frame, or even what we call the modified Dynavit-Hartenberg frame, namely a frame which is typically located at the base of the link, not at the end where the next joint is placed. And then, of course, the location of this particular frame, so its origin Ri, and, as I said there, the inertia matrix of the link considered around its center of mass. So if we put this thing together for a generic link, the dynamic parameters that characterize this link for any motion that this link may have, so in general, are the mass, mi, the three component of the vector characterizing the center of mass with respect to the origin of the frame attached to the link, and finally the 6 independent numbers of the inertia matrix around the center of mass itself. Why only 6? Because this matrix is symmetric. If we assume some axis of symmetry and uniform distribution of mass, this matrix may also be diagonal, so this off-diagonal terms are 0. But in general, we have to consider all of them. So 10 dynamic parameters. If we write down the model, as we have seen there, in the robot dynamics, there will be a nonlinear dependence, for instance, this type of things, inertia around some axis, barycentral axis, and then by the parallel axis theorem, we add mrx square, one component of the vector of center of mass. In this simple example, we call this r square of in some direction, just d square. So they appear in a nonlinear fashion, and moreover, not all of them are appearing in the model, but just some of this. Okay. So the nice property that was, let's say, discovered or formalized, better said, by Professor Khalil, a French researcher from Nantes, many years ago, that you can always reorganize the dynamic parameters in a certain way so that they appear explicitly only in a linear fashion. So the trick that we are using is somehow the reverse of what we have done dealing with kinetic energy of the link using Koenig theorem. If you remember, we have rewritten the velocity in terms of a reference frame, which is barycentral, so that we could get rid of a cross product between linear velocity of the center of mass and angular velocity of the body, so that we separate, and this is the result of Koenig theorem, the linear kinetic energy of the body from the angular kinetic energy. We will do here something reverse, just to show that the dependence is linear, and it's not really linear in terms exactly of that set of dynamic parameters that I've just introduced, but to a slightly modified set, which we will call the standard set of dynamic parameters. So the idea is the following. Again, we start from the kinematic relation, and we are dealing now mostly with kinetic energy. We will comment very shortly also on potential energy, where things are quite simpler. So the center of mass velocity is the velocity of any other point, the origin of a frame attached to the link, plus omega vector, so the angular velocity of the link vector, the vector product, so cross product, the vector characterizing the location of the center of mass. As usual, we have written this using the skew-symmetric formalism. So we have associated to this cross product a skew-symmetric matrix with the first composed by the first vector, omega I, times the second vector, RCI. And of course, if we use the property of the cross product, so if we invert the order, we obtain the opposite vector. So if we exchange the order here, we would put a minus sign here, and then if we build the associated skew-symmetric matrix now with the vector RCI, we will have a minus sign appearing there. Now, if we use this substitution in the Koenig theorem. So we worked hard to get this type of form. Now we reverse what we have done, again, just to show the linearity in terms of a new set of standard dynamic parameters. So we replace VCI with this formalism, and we have a number of terms. So we will have, in this part, you can recognize again a quadratic terms in the linear velocity of the origin of the frame that we are considering. We have still these terms appearing here, but you see that there will be also a number of cross products in which in particular this one, where you have the linear velocity vi and the angular velocity of the body omega I. If we reorganize things, we have also that this inertia matrix of the link, barycentral inertia matrix of the link, including the quadratic product coming from this term, will be added by M some square dependence on RCI. And this is the vector format of what we have written here for this single scalar term. In fact, this is the Steiner theorem. When you move, when you recompute the inertia matrix of a link from an initial expression, for instance, the barycentral expression, which is this one, with respect to three new axes which are displaced, have the same orientation but displaced by a vector RCI, then this is the formula that you get. And now, without loss of generality, the fact that we know the inertia around this center of mass or around the axis of a new frame, whatever this frame is, which we characterize with I only attached to the same link, we can baptize those numbers in the new setting with these 6 numbers, okay? So we forget about this internal dependence, and we see that what matters is the 6 numbers of the inertia matrix around the axis of this new frame. Now, here we have the linear velocity of the origin of that frame. Here we have the angular velocity of the whole link. It does not depend on a specific point. And we have this extra term appearing here. Now we will do, there's a skew-symmetric matrix in terms of this product of mass times the center of mass. We will do now some lengthy but trivial substitution here. So we rewrite this mixed term in such a way that we display linearity in terms of the product of the scalar mass times the vector of the position of the center of mass. Okay, it's not so clean, but this is the best I can do here. Okay. So let's do this product. So we have a term minus VI transpose S of MI RCI times omega. Now, we can take this row vector and write it as the transpose of a column vector. So I write just as S transpose MI RCI vector VI, and I transpose everything times omega. So I have a scalar product here. I took this, and this is a row vector, so I wrote it as a column vector by exchanging order and transposing things, and then I transpose it again. Very simple. Now, I can also write this, remembering that S is a skew-symmetric matrix. With this minus sign, I can bring the minus sign inside, so minus S transpose is equal to S. So I can rewrite this as S MI RCI times VI transpose omega I. Now remember that this represents the vector product between this vector, which is the product of a scalar mi times RCI, cross product vi, and if we reverse the order, we will change this again, the sign, so we will have S of vi times mi RCI transpose omega I. The intermediate passage, I'm skipping this. You rewrite this as the cross product between this vector times this vector. This is minus the cross product of vi times the vector mRCI, and then you write this cross product as SVI, the first vector now, times mi RCI. This is a scalar, can be put anywhere, but we will keep it there. So again, the minus sign here can be eliminated because this is a skew symmetric, so I'm rewriting this as S transpose VI MI RCI transpose omega. And then when we are times omega I, sorry. And then now we bring the transposition inside back again, and we will have finally MI RCI transpose, then S of VI omega I. So all this long passage to bring outside the vector MI RCI and leaving on one side the linear velocity and the angular velocity of this link. So we will use this property next. Before doing so, we make some consideration about the gravitational potential energy of link I, which is in general written as minus the mass of the link times the scalar product in any reference frame, typically in the zero frame of the gravity acceleration G0 vector expressed in that frame, and then in that same frame the position of the center of mass computing from the origin of frame 0 to frame center of mass of link I. Now again, by the previous vector diagram on the first slide, R0Ci is the sum of the vector going from the origin 0 to the origin of frame I. This vector was labeled just simply as Ri. You could write as R0I, but this is a more compact notation, plus the vector going from the origin of frame I to the center of mass. This could be written as Ri Ci, but again, we drop the first index I, so RCI, and then you decompose the scalar product in two terms, and you realize here that you have a kinematic quantity Ri, because this is just the location of the origin of, let's say, Dynavit-Hartenberg frame. So this has nothing to do with dynamics. And then you have the mass appearing individually, and again, the scalar product of the acceleration of gravity, which is something that you may assume to be known or not, but in this context, you assume that you know the gravity at the sea level, times, again, the same MI RCI that appears here. So if we put together the kinetic energy expression, which is now longer than the compact Koenig theorem expression, and this manipulation of the potential energy, we recognize that both the kinetic energy and the potential energy of a generic link are linear function of 10 constant standard parameter, which we organize as a vector pi in R10. So it's a vector of 10 components. Which are these 10 components? The scalar mass mi, as at the beginning. Now this combination, this product of mass time vector of center of mass. So these are three components, so not just RCI, but the product itself. Then we have the 6th component of the inertia matrix expressed in whatever new frame that you have used, not the center of mass frame. Same story for the potential energy. You find the mass, which was already there, and the product mass times center of mass. Now, in fact, the pi vector is just the scalar mi, the 3 component of mi times rci. You see that in this way we have eliminated a quadratic dependent on these terms, and then you stretch the element of the inertia matrix into this notation vector of inertia matrix of link I expressed in frame I, which is just the 6th element, independent element of this 3×3 symmetric matrix. And as a sum, you have 10 components. Now this is a row, it becomes a column once you transpose, and this will be vector pi. These parameters are called the standard dynamic parameters of link I. Not all of them will appear, but now the dependence here is linear, at least in the kinetic energy of link I and the potential energy of link I. Now, we can also recognize that this set of 1, 3, and 6 elements are the element of the so-called momentum of the link of order 0. This is the mass, so it's the integral of all infinitesimal masses on the volume of the link, so we define this as the total mass. And this is in fact the first order moment, so the mass times the components of the position of the center of mass, so this is the integral of all infinitesimal masses weighted by their position with respect to some reference frame. And finally, the second order moment is the inertia of the link. So this is a general, you don't need more than that. You could have also a third order model, mixed momentum expression, but this is all you need, these 10 standard parameters. Now this is true for the generic kinetic energy and potential energy of a generic link, but in the Euler-Lagrange equation you have to sum all this or subtract all the potential energies, so the total potential energy, and then do some differential operation in the Euler-Lagrange equation, but summing, subtracting, and doing derivative are linear operators, so they will not change the linear dependence with respect to the standard parameter pi. And this concludes the proof that says that you can rewrite the model, the final dynamic model in terms of the position pi of the vector pi, which is just the stacking of the 10-dimensional vector pi for all the links. So n link in the body, in the manipulator structure. So this is rewritten in this form. The left-hand side of our model, now we are not considering any non-conservative forces modeled through friction. So this will be included later on if we wish. So mq q double dot, cq q dot, these are linear function in the acceleration, quadratic function in the q dot, nonlinear function in q, but as a whole, if we factor out the motion variable, so q dot and q double dot, we can factor out linearly the vector pi, which is the 10n vector of the standard parameter for each link. So this is the fundamental property, and we equate this to u. So you see that if we don't know the dynamic model, the numbers to be put, we know that we have this linear set of equations, which are nonlinear in the motion variable, but linear in the unknown. And this is a strong property, because we know that we could solve a least square problem from experiment, just like we did in the calibration case of the kinematic parameters. Now this is the dynamic identification of the dynamic standard parameter. And this is a linear least square problem, as opposed to the nonlinear case there, where we expanded in Taylor expansion the kinematics equation and then reiterate the calibration by solving successive approximate linearly square problem. This problem is instead fully linear from scratch, so we don't have to make any approximation. But the story is not over. There are many things to be considered again. First of all, if we look at this YP matrix, which we call regressor for the standard dynamic parameters, we have a nice internal structure, triangular structure. Why is that? Because if we look just at the last equation will involve only the last link motion, and in this case, only the dynamic parameters related to the last link. So we have a block of 0 here, and then final row. These are all rows, which relates to the generic row equation in the model, in that model above, and multiply the parameter of link 1, link 2, link n. So we have this triangular structure. So these are row vector of size 1 by 10. So this is nice because if we have to pseudo-invert, for instance, this matrix, we can take advantage of this triangular structure from a numerical point of view. There's another property which is more buried in the equation, which you may wish to use or not. But if you look at the element of the inertia matrix M, so the element Mij, you have this functional dependence on Q and on the inertial parameters. So the parameters that appear in the column vector pi. And the dependence is like this. It depends on the index I and j. So if you have a row I, column j element, remember those elements are symmetric in the matrix, then this element will be at most a function of the coordinate k plus 1 to n, with k the minimum of these two index. So this is the functional dependence on the variable q, while the dependence on the parameters will be at most of the parameters pertaining to link from R to N, where R now is the max between I and J. So for instance, if we take as an example a 6R manipulator, and we look at the element M24 of Q, so I is equal to 2, J is equal to 4, then K will be the minimum between these two, so K will be equal to 2, and R will be the maximum, so R will be equal to 4. So we know that in this serial manipulator, this manipulator made of a serial chain of body, this element will depend at most from Q, K plus 1, so Q3, Q4, Q5, and Q6, so at most depending on this, and similarly for the dynamic standard parameter, at most depending from R to N. R is 4, so on pi 4, pi 5, and pi 6. And this is a nice check. This is a structural property that holds for serial chain of bodies. Okay, so there's a problem here. Before we proceed with trying to solve this set of linear equation with data coming from experiment, we will see how to do the experiment. But before doing this, we have to realize that as in the first example, where out of the 10 parameters, and which are equal to the 10 standard parameters once you replace the position of the center of mass with the product of the mass times this vector. So out of this 10, some of them were not appearing at all, and in fact, they are appearing, the other were appearing in a special combination that gives rise only to one number, which we will call dynamic coefficient, the only that matters in the dynamics. So those that do not appear in the equation play no role in the dynamics, absolutely no role. So we don't need to identify them. We cannot identify from motion experiment with our robot. So if they do not appear, it means that in the associated column in the regressor YP, that columns are 0. So they should be taken out from our identification process. Otherwise, we will try to cover with non-existing parameter, we will try to put numbers even there in principle. But this is not so difficult, we can eliminate this. There's another issue here, namely that the combination through which this standard parameter appear in the model. So if they are combined, it means that the associated columns in the regressor YPy are linear dependent. And this will cause a problem in pseudo-inversion, because if you have, you're inverting a tall matrix where columns are linear dependent, so they are non-zero but scaled by a constant factor, then you will try to spread your identified parameters on this without any reasonable physical meaning. So they should be eliminated in a sense, those dependent columns. So suppose that when you write down the final model, as we did for the 2R case, we will use again this example later on, you can isolate a certain number of P combination or group of standard parameters. And this number P is way less than 10n. We have seen, for instance, in the 2R case, so we have two links, so the standard parameters are 2 times 10, so 20, but in fact, all that matters are only 4 or 5, depending on how you regroup them, combination of them, what we will call dynamic coefficient. So from a regressor matrix which starts having 2 rows because we have 2 joints and 20 columns, we can eliminate many of these columns because they do not, the associated standard parameter do not appear, but then we can recombine the remaining one until we get to a number P, which is way less than 20. So this recombination is made by looking at the linear dependence. So we can partition the columns of YP in a subset which are P independent columns, and the remaining are dependent, considering also the 0 one. 0 columns are always dependent on something else. So let's partition this matrix Y in a certain subset. Then we can rearrange the order of the columns. So we put the subset into the first P columns of the matrix, and the dependent one will be combination of the independent columns. Combination of columns can be written in terms of the product of the independent columns times a matrix T, which gives the weight of the combination that gives the dependent columns. So we can rewrite things in the following way. We start with a full set of 10n standard parameters. We reorder them in such a way that we have found a minimal set, or possibly minimal set, of independent columns, and the dependent one have been put in the second part. So associated to this column, we have some standard dynamic parameters. We call them pi dependent. The other one are pi independent. So we rewrite the dependency in this way. So we combine the independent columns to generate the dependent ones. And now we bring the t inside the vector of pi. So we rewrite everything in terms of p independent columns of a more compact regressor, and we combine the independent and dependent standard parameter in this way. And we call the resulting p-dimensional numbers, we call this dynamic coefficients, not parameters, because they are combination of the parameters, and they appear as coefficient, linear coefficient in the model. Of course, the model is linear with respect to this linear coefficient, and this number, the number of this coefficient is very much reduced with respect to the original set pi. We call them A. You can use another notation, but we call this dynamic coefficient A, and there are P of them, way less than the 10 times n original one. In the literature, for instance, Professor Khalil named this base parameter. We prefer dynamic coefficient because between standard base parameters, something may be confused, so they are coefficient in the model, and they appear linearly, and there is the minimal set of numbers that we need to know in advance, maybe from CAD models of the links, or we need to identify before we can use in practice in any sense for simulation or for control problem, for design and so on, the dynamic model that we have derived. Okay? Now, indeed, this can be done, and then we may discover that this set of independent columns is still not fully independent, so this process can be repeated. In fact, we will long for the minimum number of columns that are independent, that cover all possible combination of standard parameters. The minimal number p is something that it's not immediately easy to find. You may need some inspection, some numerical test, and we will see that this is important later in identification using this linear parametrization. So let's make one example. So it is always possible to rewrite the linear model, the nonlinear model, sorry, the dynamic equation, into a regression matrix Y. Now we drop the subscript pi, function of Q, Q dot, and Q double dot, times the vector of dynamic coefficient of dimension P, way less than 10n, and possibly the minimum number. So for instance, when we have introduced the 2R planar robot, showing in particular in that case, we used the moving frame algorithm for computing the kinetic energy, and then we added also gravity in that case, and when writing the final inertia matrix and then the potential energy and gravity terms and Coriolis and centrifugal terms, we found out that in the inertia matrix there were three numbers which we call, not by chance, A, are exactly in that form, A1, A2, A3, where you find combination of the relevant standard parameters, the only that matters. And the only that matters in this combination. So my guess, and in fact this is also true, is that the best you can do if you don't know these numbers in advance is identify through motion experiment, if you don't do anything else, identify only this combination, but not the individual element inside. And in fact, this is the only thing that you really know, or really need for doing direct and inverse dynamics with the model. So there were three coefficients here, and when you're adding gravity, and you're including also G0 inside, you may take it inside or outside, so you may assume that you don't know which sea level you are working with your robot, which is kind of unrealistic, but in principle, this could be put inside, or you can put it outside. Then the coefficient remains M1 D1, M2 L1, and M2 D2, and the G0 will be moved inside the regressor matrix. In particular, we'll multiply these two columns. Okay, so this is our equivalent formulation. And when you write this, the factoring out of all function only of motion is this one. So this is an exercise that you can do. We have not done so far. So we wrote the model. We wrote it in terms of these 5 dynamic coefficients. So if we want to factor out from the equation, and this appears into the m times q double dot, and or the c q q dot, and or the g q term. But if you want to factor them out, this is the result that you get. And you see that in these columns, so this first column is associated to the parameter A1, and this column just says that this parameter is present in the first equation of the 2 equations of the 2R planar robot, and is present, in fact, inside the inertia matrix, inside the element 1, 1, because it's multiplying Q1 double dot. And similarly, the A2 parameter, which is associated to this second column, which is the most complex of them, if we look inside, we see that this A2 parameter is present in the first equation, both in the first element of the inertia matrix and in the second element, and then also in the Coriolis and centrifugal term of the first equation. Similarly, in the second equation is present in the first element of the second row of the inertia matrix, because it's multiplied in the second row, this is multiplied by Q1 double dot, and is present also in the centrifugal term. And similarly, the third dynamic coefficient, A3, is present in the first and second equation, only inside the inertia matrix. And in fact, the fact that those accelerations are not weighted by a function of q implies that this A3 dynamic coefficient will not appear in the Coriolis and centrifugal term, because it's not multiplying a function of q in the inertia matrix. And finally, those are the cosine and cosine of the sum of q1 and q2, which will multiply the A4 and A5 dynamic coefficient to generate the gravity term. So this is the final results. You could write a program that, from the dynamic model expressed in the standard form, this form, may factor out the dynamic coefficients and the associated regressor matrix. Well, this is not the unique way of doing things, unfortunately. And another consideration relates the presence of non-conservative forces. So here inside you can distinguish the torques produced by the motors and torques which are subtracted because you're dissipating energy, so friction terms. Now, if you give a model to these friction terms and bring it to the other side, you may include this into the factorization, so they will add some extra dynamic coefficients, and they will also add some extra columns to y. And the nice thing is, because of the local effect of friction, so you have, for instance, you are assuming a model of friction which contains viscous terms and Coulomb friction. So there are 2 coefficients, Fv and Fc, for each joint, and they are local. So you will add, in this case, 4 extra columns and 4 coefficients, which are exactly Fvi and Fci, because they already appear in a linear fashion in the model of friction. And you will have diagonal contribution in these columns because of the locality. You can check it out, and it's very easy. So if you're modeling also friction in this way, you will have, instead of 5 columns in the y, you will have 4 more columns. So the y regressor matrix will be 2 by 9, and you will append to the fifth original dynamic coefficient also 4 more, which are nothing else than FV1 and FV2 and FC1 and FC2, the 2 coefficients in the viscous friction model and in the Coulomb friction model. Okay, so now let's see how this heuristic way of finding dynamic coefficients can be reached also by a systematic approach. So if we start from scratch, we write down the 20, well, now forget about friction. We write down the 20 standard dynamic parameters that may appear in the model. So we have a 2 by 20 y pi regressor. And then we eliminate everything that does not appear. And then we end up at some point with a number of columns as an associated coefficient. And we look at their expression. If we assume that we know L1 and G0, so the kinematic length of link 1, which may be known from calibration of the kinematics, and the G0 is assumed to be known, then we recognize that 2 of the 5 coefficients, dynamic coefficients, A2 and A5, are really the same coefficient multiplied by 2 different known factors. L1 in the first case, so you have M2 D2 times L1, and G0 in the other case. And you see that, in fact, the really independent parameter is of the form M2 D2, so it's in the form of a first order momentum, mass times a distance of the center of mass from the origin of the reference frame. Okay, so it is one of the standard parameters. So therefore, you can do the regrouping. So you replace the second and fifth columns by just one column, the second one. And the new dynamic coefficient will be M2 D2, and you end up with a different regressor matrix times a 4-dimensional dynamic coefficient vector. Okay, so this is a minimal parametrization. Unfortunately, you can do this heuristic regrouping in several ways or follow an algorithm. So the claim is that this number is indeed minimal. So let's see if it is possible to do this in a systematic procedure, as I was saying, so following the standard parameters and then their reduction. So this is outlined in this slide. So the general procedure, as I said, the previous one was just looking at the equation and realizing some dependence. But so we start with the 20 standard parameters. We eliminate those that are not present. And pay attention. Some of them may not be present because we made some special assumption on the, say, location of the center of mass. For instance, in the model that we have derived in the previous slide and earlier in these lectures of the 2R planar robot, we assume that the center of mass is on the kinematic axis of the links, so on the xi axis, which means that there's only one non-zero parameter assumed to be present. If we assume that, in general, this center of mass may be off this axis, we should model the location vector of the center of mass with 3 components. One is out of plane, and this will never appear. But in fact, the 2 components in the plane of motion may be present. So we have made some assumption, namely that only the RSIX component of the center of mass position was non-zero, and we label this with DI in the previous equation. So eventually, we found that there are 5 parameters appearing. You see that the mass of the first link is not appearing as such, only the product of the mass times this RC1x, which we labeled as D1, then the inertia computed around the first joint axis really appear as a combination of these terms. And again, for the second link, the total mass appears now. The first order product M2D2, again, same reasoning as for the first link, because we are assuming that the center of mass is on the X2 axis. And same story, the inertia, not the barycentral one, but combined in the proper way by Steiner's theorem as the inertia around the joint two axes. Now, if we look at the y pi in this case, and I suggest that you reconstruct this for yourself, we find that the third column is in fact the sum of the first column multiplied by L1 plus the second column multiplied by L1 squared. So by two constants, which are in fact known from kinematic point of view. And this column is associated to M2, which means that we can recognize that column 3 is dependent on column 1 and 2 and replace the associated parameters with their combination, the same combination that generates column 3 from the column 1 and column 2, so with this factor L1 and L2 square. And we can regroup and reorder things so that we end up with this situation. So the four parameters are these two combination, this expression with a combination, and then A3, A4 untouched as before. And we recognize here that in fact we took the original first column and then we added to this the third column weighted by L1, and so the coefficient becomes the original first coefficient plus the previous third coefficient multiplied by the factor L1, and similarly in place of the second column and the second coefficient we have combined the second and third column, and the coefficient became then was modified by the addition of the third parameter plus the factor L1 of linear dependence. It's kind of more difficult to explain than look at the equation. But eventually we find again, through the standard procedure, the same number of parameters, although slightly differently combined, but the minimum number is again 4. Okay? Now, why we are looking for this minimum number? There are at least two main reasons. The first reason is that when we are doing experiments for identifying this parameter, having a minimum number of parameters will give us more reliable identification of this coefficient, just because we are not spreading our data with a pseudo-inverse solution, typically, over a number of parameters which are, in fact, dependent one to each other. And the second point is that the same linear parametrization, minimal linear parametrization, when we will consider adaptive control, so control of trajectory of motion, in the absence of knowledge of the dynamic coefficient, so without having done preliminarily such identification, still we can start tracking a trajectory. We will have some error at the beginning, but we will update the estimate of this unknown coefficient, and we can prove that we can converge to the desired trajectory even without having completed the identification. This is quite nice. So the controller will have a complexity which grows with the number of parameters that needs to be updated. So finding a minimal parametrization is important also for implementing efficiently adaptive on even robust controllers. So the second part of this lecture will be devoted to identification. We have everything ready. So we have linear parametrization in terms possibly of a minimal set of dynamic coefficients, and we would like to identify this coefficient through experiment. So why should we do this? Because typically the manufacturer do not provide those information to the generic user, and not even to an advanced user like research center or universities. Probably they have it in-house because they have developed the design, the mechanical design of this thing. So they have computed through CAD different parameters, then they have decomposed the link with their, each link in their elementary parts, so the motor, the transmission, heavy blocks on one part or the other of the links. So they have a fairly accurate information about this mechanical component. But they don't use the dynamic model usually. And they don't want to bring them out to the general public. So mainly they could provide only the mass, the total mass of each link, but even this is not completely known. In the data sheet, you will find the total mass of the manipulator, but not the individual masses of each link. So you cannot rely on manufacturer's data here. Of course, you can look at the structure. You may have a CAD model, purely geometric, and this is being provided, for instance, for collision checking by the manufacturer itself in their software or extended software. So, but you have to fill in those volumes of the links with mass, and you make some assumption. For instance, you assume uniform mass distribution, which is almost never the case, but it's a good approximation to start with. So you can put some number, but these numbers are really not very reliable and accurate. There's another aspect that matters. For instance, if you have modeled, and I suggest to do this in practice, also friction, then you may have used a fairly sophisticated friction model or a simple one, for instance, just viscous friction. But you should know that the number that you put there are really varying during operation because of temperature, because of wear and tear, and many things, so lubrication. So these parameters are not, so friction parameters or coefficient, they are the same as we have seen. They slowly vary over time, so you may need to re-identify things or to go adaptive with your controller. Another aspect which is relevant is when suppose that you know everything about your robot, but now the robot picks up an object, and you don't know which object this is, just because it has to remove parts, let's say, from a conveyor belt, and those parts may be anything. And you would like to precisely move things around with the payload, with the unknown payload attached to the end effector. Now, the unknown payload is another rigid body, if it's not sloppy itself. So it's a rigid body, and it has 10 dynamic parameters. Now, when you grasp it rigidly with your gripper, this payload becomes part of the last link of the robot. So the 10 standard dynamic parameters of the last link changes because of the addition of this unknown payload. And we will see later on how this change occurs. But changing those parameters will reflect in a changing of most of the dynamic coefficient in the model, even in previous links. Okay? So you have to start from scratch by the fact that you have changed the payload. And more will be said later on. So in any case, you have to start from scratch with identification experiment. So you have to move the robot and record data and use those data in order to identify the dynamic coefficient in your linearly parameterized model. So the A dynamic coefficient in the previous model with the regressor Y. In order to do this, completely different from calibration experiment. I mean, the concept is similar, but in calibration, if you remember, we position the robot in several poses, or the end effector in several poses, and we record from outside this poses with a very accurate measurement system like a laser camera system. Here, we have to move the robot. So the experiment needs to be dynamic, not static. This is very important, and it's making really the difference. And of course, you put the robot in motion, and you would like to excite as many as possible of this coefficient, in the sense that you do motion which will involve those dynamic coefficients. Otherwise, it will be hard to identify them. So the motion should be sufficiently exciting in an intuitive sense, okay? And after all, what you can hope to identify are only the dynamic coefficient, not really the standard parameters, because they don't appear, and so there's nothing to do with that, or they appear only in combination, and only the combination can be identified. So this should be well known. So how do you perform this experiment? This is quite important. So it's a general process. So you start choosing some desired motion. And this desired motion should be something that will explore all the dynamic characteristics of your arm. Let me do a counter example. Suppose that I'm a robot with my base joint, shoulder, and elbow, a 3R robot. And I will impose only this motion, whatever, a motion in this plane. I will never command such a rotation. It's obvious that any inertial parameter around this axis of rotation and associated to link 2 and 3 will never be excited, will never be involved in such motion. Only if I'm moving like this, I will tend to excite all the components. So this is intuitively what do we mean by a sufficiently exciting trajectory. So exploring the whole robot workspace and possibly involving all the components of the robot dynamic model. Well, since this, I have to collect many data from the execution or the approximate execution of this trajectory, then it's convenient that this reference trajectory is periodic so that I can move over and over, at least for a number of cycles. And this periodicity, this is another technical aspect, may be generated by assuming sinusoidal trajectories for the joint motion, so that you will repeat your configuration. But it's good to include multiple sinusoids at different frequencies, because this will excite the dynamics more. In fact, I anticipate that if the system would be linear, so in case of identification of linear system, if you have a number of unknown dynamic coefficients in your linear system, remember the robot is non-linear, but still, in your linear system, if you have a number, let's say P of dynamic coefficients to be identified, and if you're using the double the number of frequencies in your periodic trajectory, then you're guaranteed that you will get to the right values. This is, in fact, a result which holds for adaptive control, but can be adapted also for the identification. Anyway, this is kind of reasonable that you use multiple frequency, so that you don't use just set point position, but you will let joints oscillate and oscillate at different frequencies, so with a combination. So this is about the motion trajectory that you choose. Now you have to execute this trajectory. Yeah? Now, in execution, of course, we will see that if the robot model was accurately known, we could command a torque with the motor so to reproduce that desired trajectory. This is the inverse dynamic problem. But in fact, we don't have a model, a good model to start with. We are doing the identification. So the best we can hope is to follow that exciting trajectory as close as possible with a control law that is independent of the model itself so that we can implement it from scratch without knowing anything about the robot model. And the most common choice would be to use for each joint a PD-type torque command. So we will feed the desired trajectory and in particular consider the position and the velocity of the desired trajectory and build an error within the actual position and actual velocity of the joints with respect to the desired ones, and multiply this by positive gains. And typically those gains matrix Kp and Kd are diagonal, so that each torque will depend only on the local, let's say, position and velocity error amplified by the two gain Kpi and Kdi positive gain. Now, this controller will move the robot, because when the trajectory starts, even if you were at rest, let's say that this trajectory starts at rest in a given configuration, and you are at rest in that configuration, so initially this is 0, and maybe there's no gravity, so you will have an offset because of gravity. But anyway, when the trajectory starts, you will have an error, so you will generate torque intended to follow approximately this trajectory. The fact that you're not following exactly the trajectory is not bad. Why? Because you're moving close to a very exciting trajectory, so this is not the possible motion that you can generate, but it's close to being optimal in this sense. So there's no guarantee that you will follow exactly the trajectory, but you will move. And you will move not along the Q desired, so you have to measure. In fact, you have to measure where you are, even because this measure is used in your control law. So how do you measure the state? Typically, you have encoders, so you measure Q while commanding the motion to your experimental system, so to your robot in the lab. You're doing the motion, commanding the torques. So you measure Q by the encoders. But this is rarely available, you have also some tachometers on your motors mounted, then you can measure also velocity. But typically this is not the case. And you measure Q dot at a certain rate. So you have NC, a huge number of time instants. If you're doing a periodic motion for 20 seconds, and you have a sampling time where you update your command of 1 millisecond, you have 20,000 samples of measurement Q and of command U. And you store this for offline processes. Now, you store them, and offline, in order to evaluate our regressor matrix, so let's cancel this. So we have y of q dot, and q double dot times a equal u. So this is, you're providing those input because you have a control law, so you know what torque you're applying to the system. In practice, you're applying a current, and there's in the motors, there's a conversion factor between current and produced torque. So from the current, knowing the gain of this motor conversion, you have a torque. Or you may have a joint torque sensor. So you're applying a command, and then you're measuring what torque is actually going to the link dynamics. And you're measuring Q. But in order to evaluate this, and this is unknown, so in order to evaluate the regressor matrix so that you have a kind of a system, matrix time vector of unknown times vector of data, a linear equation, as you see. A very long, very tall matrix because of what we will see next. So in order to evaluate this, you have to know or to extrapolate also the information on Q dot and Q double dot. Since you have a full profile of Q, you can do numerical filtering offline of this data in order to estimate the first and second derivative of your profile. And you do this at the digital level. So if this is time, and these are the generic QI, you will have collected a number of NC samples. And now, at every instance, so this will be K of TC, the generic instant of time, or better say, let's put this with the generic instant of time. Here you have the position, but you would like to know in this instant also velocity and acceleration. If this procedure would be done online while the robot is in motion, you have not yet generated the following data, and then you can only use the previous sample in order to estimate velocity and acceleration. The obvious thing to do, if this is QK, you estimate QK dot as QK minus 1 divided by TC, first order. This is the most trivial estimation. But you can use also previous sample in order to refine this. And similarly for the acceleration, you have to do two numerical derivatives in order to get Q dot and Q double dot. But this is the best you can do online. But offline, in fact, you have also the following data. So you can use also this data in order to estimate at this current point velocity and acceleration. So you can fit, for instance, in locally through a sequence of points, and then you move this over time. Let's say some polynomial function which fit this data, and then from the expression of the interpolating polynomial, you can take the first and second derivative symbolically and obtain the expression of the position of the velocity and acceleration to be added here in order to evaluate the regressor matrix. And you may understand that your estimation is much better if you can use next future samples that you have acquired in the previous experiment. Okay? So this is the meaning of these non-causal filters. Any combination is in fact a digital filter, even that simple Euler formula. You can use 2 samples before, 3 samples before, and so on. And you can use also sample beyond in order to do this. And this is quite critical because every approximation that you introduce here will affect the solution of that linear system. Okay, so this is important. So you have Q dot, and Q double dot computed in this way. And we evaluate the regressor matrix. And of course, also the applied command. So for every instant, we have a matrix here and a vector here. And we have a set of n linear equation in the unknown A. And this for one sample instant. Of course, we have accumulated NC time instance, so we have a bunch of such type of linear equation. At every instant take K, which is K times TC, the sampling time, you have all this vector, you plug in this regressor, you have a matrix of numbers, the unknown A and the vector U. But suppose that the number of dynamic coefficient after reduction for a 6 or 7 degree of freedom robot may range in the order of 30. And here you have, for a 7 degree of freedom robot, you have 7 equations in the 30 unknown. So there's a huge number of possible solutions. Even the minimum norm solution generated by the pseudo-inverse would try to spread this experimental data over knowledge over the estimation of A. So this is not good. This is why you stack more data from successive sample of the same experiment. And you end up with a system of linear equation which has nc, the number of sample, times n, the number of joint of the robot, rows, p columns, the number of dynamic coefficients, and the same number nc plus n of element in the vector on the right-hand side. So let's call this huge, tall matrix, because nc may be of the order of 20,000 if you wish, n maybe 5, 6, 7, depending on the number of columns of joints, and p, as I said, could be of the order of 30, 40. But so you have a very tall matrix, and you're trying now to solve in a minimum error sense norm. So you're doing pseudo-inverse of a tall matrix, not of a fat matrix like we did in case of redundancy, where we were finding the minimum norm solution among the many. Here, we may not get an A which satisfies all of this because of noise and so on, but we will minimize the norm of the error in executing, in solving all this linear equation from experimental data. And here, the assumption of sufficiently excitation comes in, because if you do exciting motion and you accumulate a sufficient number of samples, then you would like to have full rank of the Y bar matrix, of the matrix made by stacking all this data one after the other. Now, if you were starting with a Y which had linear dependent columns, so you have not done this reduction, then no matter how many data you're adding, you will never get to the full rank case. Okay, so this is the reason why you have to eliminate the unnecessary or the redundant parameters and compact the columns of Y to get this rank. This rank is achieved when you're getting enough data. Okay, not for just one data. Okay, because if you have again only one sample and you have 6 joints, so n is equal to 6, you have a 6 by, let's say, 30 regressor, and of course the maximum rank is 6, it's not 30. Only if you start stacking things, then you will fill the rank in the columns, okay? And you're stacking things with exciting motion, so that you are guaranteed that this will happen. And at this stage, you do pseudo-inversion. And of course, if you have rank, full column ranks, the pseudo-inverse have this explicit expression. We have already commented on the nature, on the property of this pseudo-inversion. And why not? This is unweighted, but you can weight the solution by giving more credits to some data with respect to other data, or taking into account the noisiness of your data in certain situation, and so on. So you can use also a weighted pseudo-inverse. There's another trick. This is more technical, if you wish, so I will be very rapid on that. You can reorganize your data in such a way that you get this block triangular structure. So instead of stacking the whole matrix Y and then again the whole matrix Y at the next sample and so on, you stack the individual rows of the matrix at the current instant, at the next instant, and so on. So you start with a Y1, the first column, evaluated at the first instance T1, and then you go down for NC sample. And then you stack the Y2 and so on. In this way, you preserve the block dependence, so there are zeros here. And if you do the pseudo-inverse of this matrix, this will be numerically more robust, and also the check of the ranks will be easier in this structure. There are more practical things. Identification is an art sometimes. So, but two basic comments. Sometimes you may have outliers. So you have strange data coming from any reason, some missing reading, missing communication, some disturbance occurring and then disappearing. So if you have outliers, you cannot eliminate outliers from the beginning, not keep them into the set of data. Since you have NC data, and NC is 10,000 or 20,000 data, you can only extract portion of this. They need not to be consecutive, okay? So you can extract the best data in order to make the estimation out of this huge number of data. Similarly, if you're not including friction, or if you're including a friction model which is sufficiently complex, so if you're not going really to complexity, so you're using no model or very simple model, then, especially at low speed, you're not capturing the effect of friction. And so you're assigning your measurement to the remaining part of the model not covered by your accurate friction model. So in this sense, it's better to discard those data close to zero, where friction effects are more difficult to capture. Indeed, if you have a sufficiently rich friction model that takes into account all the details also at low speed and as well as high speed, then you can consider, as you have to consider also data when the joint velocity are close to zero. So this is the whole set of the dynamic identification. You start with some a priori knowledge, which means kinematic and geometric information about the robot. You assume that these are known. And of course, you set a target. What is the accuracy that you need? You want to have this parameter known up to 10 to the minus 3, 10 to the minus 4, or whatever. Then you do the modeling. The symbolic modeling needs to be done. So what we have done with Euler-Lagrange formalism, it's to find out the symbolic expression of the dynamic model. Without this, you cannot do identification, okay? So the model is important, and of course, you have made some assumption. For instance, you have assumed that the center of mass is located somehow on the link, for instance, on the kinematic axis of the link, and so on. And this model, this assumption will simplify the model, but may prove not to be valid for your robot. So this is a circular argument. So whatever you do the modeling, and then you design the experiment. Designing the experiment means designing the control law on a sufficiently exciting trajectory. For instance, here you see for a KUKA holding a heavy part as a payload, and the trajectory, this is just a trace of the trajectory that is being realized for acquisition of data for the identification. So you do the data acquisition, and then you process the signals, for instance, for extracting velocity and acceleration information, and then you do your algorithm of parameter estimation, pseudo-inverse, weighted pseudo-inverse, maximum likelihood schemes, and the more you have, the more you can use, and the outcome will be an estimate of the dynamic coefficient. At this point, you have to validate your estimation. So you do new experiment, and you're using now a comparison of the experimental data that you get from this experiment with what your model is predicting on this new experiment. Of course, validation experiments should be independent from the experiment that you have done for identification. If you're satisfied, you're done. So you end up with an accurate model parameters with which you can predict the torque that is needed. So in inverse dynamics, you can predict the torque that is needed for any future desired motion. If not, you have to go back, and you have to go back both. Maybe you can change the algorithm for estimation, taking into account that some data should be weighted differently and so on. Or even you have to change the design of the experiment, or back to the beginning, some parts that you assumed that were negligible should be included. For instance, you have to include a better model of friction. So if you do this, these are taken from a very nice survey paper in the Control System magazine. eventually, after identification, you have some behavior like this. For that industrial robot, considering only the first 3 joints, and measuring the torque that you're doing in a new experiment, and comparing it with the predicted torque needed for that particular motion from the identified model, you see that the difference is noisy, but practically close to 0. And then, if this is within the range of validity, of accuracy that you have set from the beginning, you're satisfied and you stop. So you have a model useful for control, for simulation. If you don't want to do experiment, you want to use this in simulation and try out some other control laws, and then bring it into practice onto your robot. So here we have done this for several different robots. So these are experiments with the KUKA lightweight. We model this. We end up with 30 inertial parameters and 12 parameters related to gravity. So 42 dynamic coefficient, in fact, not parameters, sorry, out of 7 times 10, 70. So we have half the number of standard parameter converted in combination of dynamic coefficient. And we made this type of motion, and we acquired motion. We acquired from this motion data. The fact that this motion is relatively slow, it's more technical, but anyway, we are exploring different configuration and also with motion. And at the end, we estimated this parameter, and then we make other motion, a validation for all 7 joints. Here you see the 1, 2, 3, 4, 5, 6, 7 torques. This robot is equipped with joint torque sensor. So what we are doing is we are executing the new trajectory based on the model that we have identified, and we compare the commanded torque with the measured one from the joint torque sensor. So if we are really doing the motion in the right way. And you see that there are some residual error on some joint. Pay attention to the scale, because if you look at joint 3, the torque, the green torque, which is the computed one, is superposed to the measured torque, but the scale is 40 newtons. Here you see some error, but here the scale is 2 newtons. So you are, by and large, for each joint, you have a residual error which is below half a Newton meter. Okay? And this is quite satisfactory for this type of robot. Now, for instance, you could also separately identify gravity. So, for instance, if you move around and stop, at this stage, only gravity is present in the model. If you acquire data only from different configuration where you are at 0 velocity, then those data should be used only for the gravity term, because velocity and acceleration are 0 there. Okay? So if you look at the gravity term G of Q, this can, each individual term in the model can be linearly parameterized with coefficient. Here we have a set of 12 coefficients which appears only in the gravity, or at least in the gravity term. And you can recognize some are first order moments, so the product of masses time center of mass, plus you have D1 and D2 are the only 2 kinematic parameters. Here I'm using the notation of, these are the only 2 non-zero parameters in the DH table of the KUKA lightweight robot. So these are known, and here you see some of masses of the various links. So this is the symbolic expression. So we acquire data in different configuration. We have the applied torque. There we have the explicit form of the dynamic coefficient and of the associated regressor matrix. So this regressor matrix will be 7 by 12 matrix, because there are 12 symbolic parameters in the gravity term. And we do this for several different configurations, and then we end up with an estimation, a pseudo-inversion of the stacked y bar g, so the yg evaluated at the different configuration, and we end up with this vector of numbers. Some of these numbers are close to 0. You see 10 to the minus 4. Some are pretty different from 0. Now you can decide to discard those parameters which are below 0 or take it into account and then do the validation. And if we do the validation and we look just at the gravity torque, you see that the prediction is quite accurate here. So now, what about friction? The first experiment that we did on the KUKA were not considering friction. In fact, friction on the link side of the transmission is quite small, but still present. So we did a first set of new experiment with dynamic motion, and these are the comparison between the estimated torque for the realized validation test and the one measured from the joint torque sensor. Actually, those were also filtered because the joint torque sensor itself maybe introduced some noise. So these are the filtered version and without friction estimate. You see that, for instance, joint 3 is quite good, but joint 1 and especially the last 3 joints and also joint 4, you see some discrepancies. Again, look at the scale. We are always below 1 or half Newton meter. You don't see it here. Probably you have this discrepancy even here, but here for joint 2 and joint 3 seems everything perfect. For joint 1, you see the range is between -2 Newton and 4 Newton meters, so you can tell there's some offset of 1 Newton meters or so. And this was done by comparing the blue profile, the filtered measured torque, with the torque produced when you're doing the motion Q, Q dot, Q double dot, and Q dot and Q double dot are computed offline, where inside the inertia matrix, the velocity vector and the gravity vector, you have plugged in the identified dynamic coefficient from the previous experiment. So you're predicting a torque tau, and you're comparing with the torque tau mesh. The green and the blue line refers to the color of the plots in the graphs. Then we decided to add, in order to capture this missing part, to add also a model of the friction. So we assume that this is the situation. We give a specific model for the friction, and we bring this to the other side so that in the identification, we are identifying also the friction terms. Now, this can be done in single stage, so identifying everything together, including the dynamic coefficient in the friction model, or in 2 stages. First, you identify everything without friction. Then you use this as a priori knowledge, and you identify only the extra friction terms. We have done both approaches. We have used, if you can see, a very special model for friction. In fact, this has some sigmoidal function, some exponential with parameter phi1, phi2, and phi3, and this is known in the literature because we wanted to capture some smoothness close to 0 velocity. So a standard model with viscous and Coulomb friction alone was not able to capture those. And you see that if you compare just visually the right plot with the left plot, you see some reduction in joint 1, again, perfect reproduction in joint 2 and joint 3, but even here you see that now the model is closely following the measured data. And this is because we captured the missing part with this friction model. So this is now state of the art. We are using this model of the lightweight robot for all experiments that we are doing, which involve the use of dynamic model in the lab. So this is a video instead taken from the group in Nantes, in particular the laboratory of Gauthier and Khalil. Khalil is no longer in life now, but and you will see essentially same concept, but here they are doing faster dynamic identification experiment. So here you see the typical speed at which the robot moves for acquiring data. Again, you are only acquiring position data. So you're generating velocity and acceleration data that you need for evaluating the for evaluating the regressor matrix offline from this numerical differentiation as I explained on the blackboard. Okay, so this is an idea of the behavior. Now let me conclude with some variants. For instance, what if we have identified perfectly our robot in free motion, and now we add an unknown payload? And why do we do this? Well, for several practical cases. For instance, typically in an industrial setting, the robot changes tool for performing new operation. And the tool has different masses, different parameters, and you may not wish to identify everything a priori. And the other typical case, if you do the pick and place task with objects which have unknown mass a priori, just because you're removing parts, let's say, from your workspace, and you don't know the mass of this, and you would like to place it in some prescribed position, so you would like to be very accurate. So there are a number of reasons when you would like to have an identification or an improved identification in the presence of an unknown payload. So starting from a good model, but now adding this payload. One reason is that the model, as we will see at the end of the course, will be used also for collision detection. So for automatically recognizing the presence of a contact without using extra sensor, using just the model. So if the model is very accurate, including a possible payload, the collision detection capabilities using this model will be higher. So with this in mind, just pose two questions. If we add this payload, does the system changes dramatically? And in particular, do we obtain again a linear parametrized problem in terms of new dynamic coefficients? The answer is yes. And this is more technical. Does it make a change if we are representing things with respect to a Denavit-Artenberg reference frame or some other modified frame? No. As long as you do one thing for the payload, which is common to whatever reference frame you're using. So now we add the payload. So we said that since we are grasping the payload rigidly, or this is rigidly attached to the end effector, then the 10 standard dynamic parameter of the last link will change because the last link will include also the payload. Now, suppose that the last link has the following standard parameter. A mass Mn, n stands for the last link, a vector that goes from the origin of the frame attached to the link to the center of mass, which is called Cn. By the way, this is not the standard parameter. Only Mn times Sn will be, Cn will be the standard parameter, and some inertia tensor expressed with respect to frame n, not to the center of mass, remember. And same story for the payload. So a mass ml, a center of mass cl, and inertia, but pay attention, we characterize the position of the center of mass of the payload and the inertia with respect to the same last frame of the last link. So this is important, because otherwise the following equation will not hold. So what happens to the mass of the last link? Just add the mass of the payload. Symbolically, and then you will identify the new combined coefficient. What happens to the center of mass, in particular to the moment of the first order? So for every component I, x, y, z, so this is a scalar mass of link n multiplied by the vector going from the origin of frame I to the center of mass of link, origin of frame N, sorry, to the center of mass of link N before adding the payload, then this will become the following one. First, you take the balance of two masses. So two masses of different weight, and each with its own position will generate an average, a weighted average for the resulting center of mass, and this in all x, y, and z direction, multiplied by the total mass. Now, if you simplify things, you see that you simply sum up the first order momentum of the link N and of the payload when both are expressed with respect to the frame of the link N. And same story for the inertia tensor. So you will just sum up this because they are both expressed in terms of the same reference frame, namely the reference frame of link N. So you don't have to add any reference frame for the payload. This is the whole story. Linear parametrization through this equation is obviously preserved. So this is our situation. Here we have again the 2R robot, and we have a payload. Now pay attention, the payload now is represented as being perfectly balanced with respect to the gripper. So its center of mass is on the x2 axis, but in fact this needs not to be the case. Similarly here, the center of masses are assumed to be, in the picture, are assumed to be on the kinematic axis of the link. So the center of mass of link 1 on the axis x1, which is the frame attached to link 1, and the center of mass of link 2 on the axis x2 of the frame attached to link 2. But in fact, here, when there is no payload, so the unloaded case, for this case, we have seen that 4 parameters would be enough if the center of masses were on the kinematic axis, while here you find that 6 parameters appear, because here I have included also the possible presence of an offset in the y direction of the center of mass, which means that this center of mass may be outside the kinematic structure. Of course, this is just the skeleton of the robot. No? You should imagine the full body so that the center of mass can be also outside this line. So with these two, if you assume that they are in fact on the axis xi, C2y and C1y will be 0. So from 6 dynamic coefficient, you will come back to the minimum number of 4. Why did we include this? Because in general, when you add the payload and the payload is off-centered, then you will have to modify also these parameters. In fact, when you load the end effector with the payload, you will have this type of modification. As I said, you add to the mass, to the product of mass time distance to the center of mass, you will add this one. When you had the single mass multiplied by A1 and A2 are the link length, so our kinematic parameter. So M2 is replaced by M2 plus the mass of the payload, and same story for the inertial terms. So exactly the same rule as before. So you know how to modify the structure of the symbolic terms without redoing all the factorization. This is the message. You had the factorization, you had the dynamic coefficient, you just look at the dynamic coefficient where parameters of the last link are present, and you modify those parameters according to the rule of the previous slide. This note was already commented, and same story for the expression of the kinematic frame. So this is a video of an experiment. You will see here an experiment in which we do the identification, the extra identification with very small motion. So we started with a full model of the robot without payload. So the robot is without payload now. Now it's starting here you see the interface on the computer. So Claudio is adding 3 kilograms of payload and fixing it to the end effector on this support. And now the robot will perform some extra identification of the parameter of this payload. So we know in advance the payload, but we do now this small motion. In fact, we're interested here mainly in the gravity part. So we would like to identify the mass of the payload and the standard parameter of the center of mass multiplied by Mn. And once we have this, to validate the fact that the robot is able to detect collision with the new model, including the modified parameter due to the payload, Claudio is touching the robot and the robot is stopping, recognizing the collision without any extra sensor. And we will see how to do this in the block of slides related to collision detection. Let me conclude with a number of reference papers, 2 surveys, the one that I already cited, the second is from the Springer Handbook of Robotics, and then a number of papers that we have been working in the last few years. And in particular, I'm using a color code, and I'm referring what we did. We identified dynamic model for the KUKA, which is a 7 degree of freedom all-revolute joint in the lab. We did the same thing also for the universal robot, which is a 6R robot in this paper, where the name of the universal robot is not appearing, but we use a model-based residual approach for collaboration, for estimating contact forces. So we were using the dynamic model. And in this case, while in this case you have joint elasticity, in this case the system is fully rigid and friction is very relevant. So here we made a huge effort in order to include also a correct identification of the friction terms in the model. And lately we did the same on Franca e Mica with a collaboration with the CNRS Center in France. We don't have yet a Franca e Mica Panda robot. I hope we will have it soon. In this case, if you trace this paper, you can find also source code. So we made available all the algorithm and the data that we collected for the general public. So if you trace in Explore this paper, you can download also supplementary material that describe this. So with this, we conclude this part, quite detailed part with respect to what you find in the book. So please make reference to the slides for your preparation. Thank you for listening.